Let's hear your questions.
Roughly, how long did the first stars live for?
Yeah, so I think the answers we're not exactly sure, but probably millions of years. So that sounds like a long time, but a star like the sun will last for about 10 billion. So it's a lot shorter than the stars we have today.
Right, next question. How about over there?
Very good question, by the way.
Shirt.
If we live in a multiverse, does that mean that the beginning of the universe we live in might not be the original Big Bang, but just our particular universe at a later time?
So if we live in a multiverse that was a universe that was created through the process of inflation, we have every reason to think, now we have an incomplete theory of inflation, but we have every reason to think that inflation would have continued forever, spawning universes forever. So we could be anywhere along that line. It's possible that inflation never even began, but just is a continuous process for infinitely far back in time. It's only speculation, but that seems consistent to me. It's even, I'll hesitate to say this, but it's even possible that you could imagine a universe like ours going on to eventually have another inflationary age in the future that created the inflationary phase that eventually created our universe.
Right. Any questions on this side, maybe? Yes, over there. Just wait for the microphone. There should be one coming. Oh, sorry to make you run. I dispatch side to side, but and I'll come to you upstairs in a minute, so get ready. Just over here.
Hi. So if the universe is constantly expanding, what will happen if eventually the galaxies get so far apart that light can't reach us anymore?
Yeah, the future of our universe is kind of a bleak one. So we have this cosmic horizon beyond which nothing can reach us, and that's just going to get closer and closer and closer. Like 100 billion years from now, we'll be in a state, well, first of all, the Milky Way and all its kind of nearest neighbors will have all merged by then into one giant galaxy, and we won't be able to see anything else. That will be the only thing we can see when we look in the night sky. So right now, I give you these pictures and there are galaxies galore, right? 100 billion years from now, there will be nothing like that. If dark energy is truly constant and it never changes, that will be kind of the end of the story. If it increases even a minuscule amount faster than that, so if it's not really constant but increases slightly with time, which is still possible, then even that super galaxy will get torn apart as space continues to expand. Ultimately, the solar system would get torn apart. Of course, our solar system won't live that long, but solar systems will. And eventually, things like planets will get torn apart into individual atoms. And then those atoms will get torn apart all the way down to the smallest subatomic particle. So it's going to be a hard place to live in the end game.
All right. Do you have any questions from upstairs? Yes, just...
How does supersymmetry link to the constant expansion of the universe?
Wave your hand so I can see who I'm talking to.
Over there.
Oh, in the top. I didn't even know there was a...
Top.
Okay, right. So supersymmetry is a theory that's been hypothesized since the 70s. There's been a ton of interest in it. I'm one of many, many, many people who've written a lot of papers on supersymmetry. It's one of these theories that looks just so good and solves so many problems all at the same time that even before you observe any evidence of it, you think, oh, this has got to be true. What it predicts is that for all particles fall into one of two categories. They're either a boson or a fermion. The quarks and leptons are all fermions, the others are all bosons. And according to supersymmetry, nature can't have one without having the other. So you take the electron, it's a fermion. It says there has to be a supersymmetric partner of it that's a boson. We call it a selectron or superelectron. It has the same electric charge and same other characteristics. It might have a different mass. It does have a different mass if it exists. And then you have the photon, which is a boson. It has to have a fermionic counterpart. We call it the photino. so on and so forth. Supersymmetry is great, except for the fact that we've never observed any of those supersymmetric particles. I thought it was pretty likely that the LHC would turn on and we'd discover them for the first time, or at least some of them, but it hasn't. Maybe it will in its next run. But I think it's fair to say that whereas supersymmetry was super popular 10 years ago, its popularity is waning now. People are a lot less confident supersymmetry is real. How it connects to cosmology is that supersymmetry provided us with one of our very best or favorite preferred dark matter candidates. The supersymmetric partner of particles like the photon, Higgs bosons, and Z boson all become things called neutralinos. And those neutralinos have all the characteristics you want in a dark matter candidate. They just work really well as dark matter, but we haven't seen it. Neutralinos probably aren't the dark matter now, although there's still a sliver of hope.
Excellent. Did you have a question on this side, maybe, just to mix it up? Up over there, maybe? Yeah.
So you know how you said it would look the same if everything was expanding as if it was all shrinking at the same time?
Right.
How do we know it is expanding and not shrinking?
Well, I think, strictly speaking, we don't, okay? I'm going to put my philosopher of science hat on now. I'm going to even posit that there's no difference. Two theories which in every possible respect predict all of the same things aren't different theories. There's just two ways of thinking about the same thing. Now, bear in mind, though, the theory where everything is shrinking in unison, I really mean everything. That's a lot of things to kind of coordinate. So the speed of light has to be shrinking. The forces that hold protons and neutrons together in atoms, they have to change in just a way to cause the atoms to shrink at the same rate. And those have nothing to do with each other. So it's quite a coincidence. And I could list many other things that all have to shrink or change in the same rate to mimic the effects of the expansion of space. So if I had to speculate which one of these is really going on, I would say that space is expanding. For one thing, Einstein's theory says it has to be. But I won't quibble with you too much if you insist on saying all of the material in the universe is shrinking instead.
Right. You have a question? Microphone's coming.
You were saying that protons and neutrons were created in a fraction of a second after the Big Bang. But why weren't atoms heavier than iron formed then? Surely there was enough energy around at that time to create all atoms.
Good. So there's plenty of energy. That's not the problem. The problem is there's so much energy there that if you drop the iron nucleus into it, it would fall apart. Iron is way too fragile to survive the first millionth of a second after the Big Bang. So the first time that our universe really had the conditions that could make something like iron were in relatively early stars, not the very first stars, but stars not long after that through nuclear fusion you could slowly build up heavier and heavier nuclei. Iron has so much binding energy, it's the end state of a lot of cores of stars today.
Just a question about the scale of dark matter. I understand the idea of you can detect dark matter because of Andromeda and the spinning of the outer solar systems. Would it affect at all the rotation of Pluto? Because that was found by looking at the rotation of things and being able to pinpoint it because of that before they knew anything about dark matter.
So the best place to look for signs of dark matter is where there's not a lot of mass in normal matter. The solar system is not that. The solar system, by definition, has a star in it. And that means it's in an abnormally high density region of normal matter. So the sun just swamps any dark matter that would be here. We just can't detect it. If it were here, we wouldn't know. So we assume we're being bathed in dark matter right now, but we can't empirically tell one way or the other.
When you say we have an incomplete theory of inflation, how incomplete is it? Because we seem kind of vaguely confident that it happened, but we don't really know kind of the ins and outs.
All right, yeah, let me expand on that a bit. So I think we have good reasons to think that inflation or something like inflation probably happened. That's about as confident as I'm willing to be. There are really good cosmologists, smart people who are studying this sort of thing for a living who would disagree with that. They would say, no, inflation's got deep problems. Here's my other theory that I offer instead. The consensus view is that inflation's our best theory, but very few of us will say we're certain that inflation happened. When inflation was predicted in the 80s, it made a number of fairly specific predictions about the patterns of light we would see in the cosmic microwave background. I'll use a little bit of technical jargon here, but we predicted, or it was predicted at the time, that those temperature variations would be adiabatic, Gaussian, and nearly scale invariant. Don't worry about what those three words mean, but all three have turned out to be true. For that reason, many cosmologists who were originally skeptical of inflation have come around to thinking that probably happened. That's about all we know, okay? If you pick up a review article in a journal on inflationary theories, it will list in theory after theory after theory after theory. They took place at different points in the early universe. They involved different kinds of energy fields or particle content, and they ended in different ways. So there's a huge array of possibilities. We're slowly testing them with observations. And I would say in the next 10 years or so, observations of the cosmic microwave background are pretty likely to measure some important stuff that allow us to narrow that search. For example, we're going to measure something called B-mode polarization, or at least we hope we are. This has not been measured in the cosmic microwave background to date, but if we do measure it, we'll be able to tell you how high the energy density was during an inflation. That would be an incredibly powerful number to have. Also, we're looking for something called non-Gaussianity, which should be really small in inflation, but not precisely zero. So if we were to measure that, again, we could narrow the range of models down dramatically and also be more confident that inflation really took place.
Right. Do you have a question from above? Yes. Balcony.
Hi. What's your opinion on the discrepancies in the measurement of the Hubble constant?
So when we measure the Hubble constant in kind of our cosmological neighborhood, we get one number, about 73 kilometers per second per megaparsec. And when we use the cosmic microwave background and other early time measurements to infer what we think the value of the Hubble constant should be based on that, we get a number that's not 67, not 73, but more like 67. These are really different because the error bars on those two measurements are so small that they both can't be right. It's possible that somebody's just measuring it wrong. In fact, probably that's the most likely answer, and that will get resolved in the years ahead. It's also possible, and I've been working on things like this, but it's possible that there were other forms of matter and energy present in the first hundreds of thousands of years of our universe that would change how we infer the Hubble constant from that early time data. And it could change it enough to bring these two numbers into approximate agreement. And that's what I'm cheering for. That's what I'm hoping is going on. I'm hoping there's some sort of energy density that we don't currently know about, some new kind of particle species that was abundant then that skewed things just enough to bring these two numbers into alignment.
If there's a multiverse, then is it possible that the multiverse could have had a Big Bang as well?
Sure. If we had a multiverse that came into existence through inflation, it's possible inflation just continued in forever in all directions of time. It's also possible it started. Maybe there's a Big Bang that took place at a singularity in space-time, the kind that Stephen Hawking used to talk about. And that happened once, and right after that, inflation started, and that led to the multiverse, including our universe. That's a totally consistent picture, but I'll warn you, there are a lot of consistent pictures. We don't really know. Good question.
How do you measure time in an inflationary universe?
Yeah, so the kind of people who work on inflationary theories have several kinds of time in their theories. There's something called conformal time, and then the kind of time we might talk about. So it turns out to be a kind of a nuanced question. That being said, there's nothing preventing me from hypothesizing something like a clock. okay? You know, some sort of timekeeping device. Maybe it's a particle with a certain half-life, and I watch how much of it decays. And over the course of inflation, I see how much of it decays, and I use that as my measuring device. That's perfectly consistent. One can do that. So yeah, I think the answer is the same way you would measure time or talk about time in any other physical context.
You were saying that you look one way in the universe and the other way they have the same results because they were very close together at the beginning. How could you possibly explain them not being able to talk to each other without massive inflation? Because otherwise...
So in other words, what you're asking, what other theories are there to compete with inflation?
How could you separate those two particles so after 13.8 billion years they couldn't have talked to each other?
So one kind of alternative to inflation that has some serious challenges and hasn't been very successful yet, but smart people are thinking about it, are cyclic models or bouncing cosmology models. These are models where the universe expands, stops, contracts, bounces, and expands. That means in the past, everything was in contact at some point in cosmic history, solving this problem.
But sorry, I still don't understand how, if they were in contact, but then they had light travels fairly quickly, how could they not have spoken to each other through light in all that time?
Sorry, I misunderstood your question, I apologize. So it's simply a matter that if, let me put it this way. We're surrounded by a horizon. We can't interact with anything outside of that horizon, and we never could and we never will, okay? That point, horizon reaches just about to where I am now, and that point's horizon reaches to just where I am now. They are both outside of each other's horizon. So they never had a possible opportunity to interact. Light couldn't travel that fast. Nothing could.
But I guess that's where I'm coming from.
Yeah.
So they were close together at some stage.
In inflation, they would have been, but in the standard Big Bang theory, they never were. Let me one more thing. So people think that in the standard Big Bang theory, that the universe was very small at some point. That need not be true. It could be that our universe goes on forever in every direction. It's infinite in scope. And in the past, we could go back to a point a few 100,000 years after the Big Bang, and everything was 1,000 times closer than it is now. But still infinity. And I go back arbitrarily farther, and everything's closer and closer and closer. It doesn't mean that point was ever close to that point. And even if they were kind of close, they were only close for such a short period of time that light can't travel very far.
Right. Just 2 rows down right here.
In regards to the matter-antimatter imbalance, do you have any hypotheses as to what would have caused it?
Yeah, I do. But the reason you should take it with a grain of salt is that if you find any particle cosmologist, they will have written their own theory too. And most of us aren't right. I wrote a paper like 15 years ago positing it was actually a supersymmetric theory to build on the other question before. I think, in fact, the theory I wrote down to explain it is now falsified. The LHC didn't see the particles we said would exist, so we weren't right. But that's okay. We're in good company. I will say that we kind of know what sort of things have to be in any theory that will do this. These conditions were laid out in the 1960s by the Soviet physicist Andrei Sakharov. He worked out that any theory that could explain this problem introduces some new kind of interaction we'd never observed that changes the net number of protons and neutrons, or quarks if you prefer. Also, we know that those interactions have to happen in a way that favors antimatter becoming matter over the reverse. Okay? Otherwise, the two processes would just wash each other out. And we know these interactions must have taken place in a particularly volatile setting. Maybe there was some sort of dramatic phase transition that happened in the early universe while these interactions were at play. Maybe there was some kind of heavy particle that stopped interacting with the bath of particles around it, and then waited a while, and then spontaneously decayed to produce mostly matter and not as much antimatter. Those are the sorts of things that might have been responsible. But yeah, no one really knows.
Can you say anything at all about the few seconds before the Big Bang?
So here's the trick, okay? When we talk about the moment of the Big Bang, the space-time singularity at time equals 0, this isn't some arbitrary point on a timeline. This was the first point in the timeline. Asking what happened before the Big Bang is like asking where on a map is north of the North Pole. It's not a cogent answer to that question. If you read the work of Hawking and Roger Penrose, they actually proved in using general relativity and from certain kinds of principles involving quantum physics that if you run those equations backward far enough, you will reach the space-time singularity where time and space kind of become like each other, okay? And they have a boundary, a curved, smooth boundary. There's nowhere you can go on that manifold of space-time that gets you before t equals 0. That's why I don't talk about before the Big Bang. I want to say, though, that we know so little about the early universe that I find it conceivable that everything I'm saying about that era of time will be overturned one day. But to the best of our current understanding, what I'm telling you is the consensus view.
Yes, please go ahead.
So on the our standard model, you've explained 3 of the 4 fundamental forces. So why has gravity why can't we find the fundamental force or the reason for the fundamental force of gravity?
Yeah, let me go to that chart for you. Here we go. All right, so on the right side are the particles that communicate the force of electromagnetism, the strong nuclear force and the weak nuclear force. Gravity is conspicuously absent. That's because we don't know how it works on a quantum level. There's probably some quantum force carrier that communicates gravity, call it the graviton. We've never seen a graviton, and frankly, we don't have a clue how one would ever see a graviton. It'd be a very hard thing to test. And we do know that when we take what we know about quantum physics and we combine it with what we know about general relativity, at least one of these theories is broken, at least insofar as you can't apply it to arbitrarily high energy conditions. One or both of these theories breaks down, and presumably these 2 theories get replaced by some grander, more complete theory, call it a theory of quantum gravity. Maybe it has something to do with string theory or loop quantum gravity. I don't know. I certainly don't know. I don't think anyone knows. And that theory will address all these questions. But it's not on this chart because this is a chart of things we've observed, things that we can study, things that we understand. And quantum gravity is not among such things.
Right. I'd like to hear a question. If you're sitting there think I have a question, but it might be silly, it might be a stupid question. Usually these are the absolute best questions, so don't hesitate. Raise your hand. Who has such a question? How about here? Let's hear a question.
It's a question about black holes.
Excellent.
What happens inside one?
What's inside one?
Yeah. What happens in there?
Excellent. We need to make him work for this.
I'm not sure I'm going to exactly answer your question. I'm going to say some things like adjacent to your question. All right, so we know how to make a black hole. All you need to do is put enough mass and energy in one place at one time. General relativity will do the rest. All a black hole is something that has so much energy and mass, or just think of it as mass, I guess, that it curves the space around it so dramatically that the curvature reaches infinity, and even light can't travel in or out. Okay? When very massive stars explode as a supernova, the thing that's left behind collapses into a black hole. We also know that every galaxy, or just about every galaxy, has at its core a supermassive black hole. Like our Milky Way has a galaxy in its core that's a few million solar masses, a few million times as massive as the sun. Some even have bigger black holes than that. We're starting to have an understanding of the quantum nature of black holes. Hawking showed a long time ago that the information stored in a black hole is proportional to its surface area. It was a little weird. You should think it's volume, right? If I take a box of gas, the information stored in that is proportional to its volume. But black holes are different. That has led to a series of ideas involving holography. The idea that things like two-dimensional physical theories can be identical to other seemingly very different three-dimensional theories. So that raises the question, is our four-dimensional space-time really a five-dimensional other theory that we can't even put our heads around? And as far as what's in a black hole, there's something called the no-hair theorem, which says that other than the mass and charge and rotational rate of a black hole, there's literally nothing else that distinguishes one black hole from another. So if that's true, then you really can't say anything at all about what's inside a black hole. That information's been erased forever from the universe somehow. Or maybe it's encoded on its surface, depending on how you think about it. Jason, close enough?
Right.
If there was a space-time...
Singularity?
Yeah, that's what I was about to say. I just forgot my words. If there was a space-time singularity with infinite density, then two or three questions. One, why do we not live in an infinitely dense place today? Two...
Let's focus on maybe on this one, or just pick your favorite one, because
how can something have an infinite density and still a physical appearance? It is there, but not nothing, but infinitely small.
Yeah. So one thing I learned as a physicist a long time ago is not to lean against fragile things, is that just because something seems really counterintuitive and seems like it can't be right, doesn't mean it's not real. If I insisted that everything about our universe kind of follow my intuition, kind of make sense in my gut, I would have never accepted the theory of relativity. I never would have accepted anything I currently know about quantum physics. Those things are so weird, but that's how the world is. So, could there be an infinite temperature and density space-time singularity that started off the Big Bang? It seems really far-fetched to me too, but that doesn't mean it couldn't be true. And Hawking and Penrose showed that if you take a space-time like ours and you let it evolve backwards, that's what you get. So maybe that's the answer, but I want to caution you, we don't really know. Nothing that happened in the first second we're really sure of, and certainly nothing that happened at t equals 0, if there ever was a t equals 0, is something we can say with any confidence actually took place. Good question.
All right, we have time for one more. How about right over here?
All right, last question, make it a good one.
No pressure.
No pressure.
Towards the beginning, you said that the universe in its first seconds is about 3,000 degrees Kelvin, and now it's about 2 degrees Kelvin. Is there a chance it's ever going to reach 0 Kelvin, and what would happen then?
So, if I take one photon, traveling through space, and I stretch that space, so I double it. I double the length of that space. That will double the wavelength of that photon, which will cause its energy to go down by 2, and the temperature of any collection of photons as part of to go down by a factor of 2. So if I make the universe 1 billion times bigger in linear dimension, then that 2.7 degree Kelvin will become 2.7 divided by 1 billion Kelvin. To reach true 0, of course, would require you to expand to an infinite length, some infinite time in the future, but we will asymptotically get closer to that temperature of 0 as space continues to expand.
Well, that's something to look forward to.
Yeah, cold death.
So there were still lots of hands up. We're running out of time, but I have a great solution. On the way out, you might be able to pick up a copy of Dan's book, which might very well answer your burning questions. Otherwise, Dan will be hanging around outside there signing books, and I'm sure you can approach him with any further questions. So all that's left to do is to thank Dan for a wonderful evening and talk.